Right. Okay. So first of all, we ran out of time from the previous one, and we're gonna go a little bit faster. Right. So if you remember, the other day we did like probably the simplest model, which was learning about proportions, and just that simple model, when we were trying to answer a bit more sophisticated questions, that already forced us to introduce simulation methods, right? So that's the we're gonna move into that direction. The idea is that through simple models, first of all, we'll learn the basics of Bayesian methods, and the second one is that these methods, these models, which are even that they are simple, they will force us to gradually force us to introduce the computational machinery that will require when we go to more complex models. So today we are going to focus on means, inference on means in the first part, and the type of models that we shall be using are called normal models, right? So this guy's not working. Right. So today, well, we do means and then regression, and in the lab, the last part of the lab that we have is has an ecology example that is kind of interesting if you want to do. Okay, so that's the kind of problems that we do. It's that we shall be talking about. Is we want to talk on inference and prediction over means. And that would be a typical example, like we are trying to detect fraud in fishing. So there's some type of regulations in the European Union that require the sardines to be of size bigger than certain size, right? I mean, suppose that this is we capture a boat which is called Ayuso at the entrance of the port. And we would like to assess whether this crew is not respecting the regulation, right? So there's a numerical example in the lab, right? As I said, and we just go through the concepts here, so that if you want to do it, you can follow it.
So suppose you.
Yeah.
Suppose you catch a fish that's shorter. Are you supposed to throw it back to the sea, or?
Yeah, that's the idea.
And they survive.
Yeah.
Okay.
I mean, it depends on the type of fish, but if you do it with nets, etc., the idea is that you have to give back. And here the idea is you would expect that well, they make some mistakes, but are they consistently going below that? So basically, we would like to test whether the fish. We'll take a sample and we'll try to assess whether the average size of the catch that they have is smaller or bigger than that size. Okay, so for this we're gonna work through the normal model, right? So first, MLE inference, just as a quick reminder, and that's something that we've done in the previous course. But basically, we want to learn, and we're going to make it like in a sort of template way of thinking, right? So we have the parameters, which in this case is this guy, which appears here is the mean, right? We have a model, so observations given parameters. In this case, it's a normal with a mean, and in this example, in this case, that we shall assume that this variance is known, somehow known from previous studies. So we formulate the model like this. we get data, and the first thing that we need to do is get the likelihood. So which in this case is quite standard, and typically the idea is that we get this we multiply these probabilities or these densities, and the idea is that we remove everything which does not depend on theta, right? I mean, this is proportional to this quantity. And then we'll typically compute the logarithm of the likelihood, and then we optimize. And basically, that's what we have been doing. Oh, okay, basically that's what we've been doing in the course. So we compute we check whether this is a maximum, and that's in this case, which is very classical, the maximum likelihood is this. Now, when we do Bayesian inference, we have quite frequently, we try to take advantage of other information that we might have to make it a little bit easier. In this case, we're going to assume that this information is non-information. So we can model probabilistically the lack of information. So we're going to use a non-informative prior. So the prior that we're going to use the prior information that we have about the parameter is, in this case, is flat, right? So it's an improper prior. We say that this is improper because it doesn't integrate into one, right? Okay. And now the update in this case is we compute the posterior distribution, so the distribution of the data given the parameter given the data, and we just I mean, how we proceed is we just would multiply the likelihood on the prior, and then we try to get rid of everything which doesn't depend on theta. In this case, is the same. And then our aim would be to try to recognize some type of distribution. This will typically be not possible, but in this case, we recognize we have an exponential with this quantity, and there's a theta square, etc. So we recognize that this is a normal. So the update in this case is we move from this, in which we didn't know, we had no information, we declare no information in this case, we move to this, we have updated it to a normal, to this normal distribution. Okay. Right. So one important thing that we shall, one interesting advantage that we shall mention several times is that we don't need to learn in batches, so we can actually perform, we can learn sequentially. So here we just put the recurrence between the posterior mean when we have n+1 data with a posterior mean when we have n data, right? So, and again, the same, the relation with the variance is there. So it's sequential. Okay. Now, in many cases, we might have actual information coming from other studies or from experts, etc. And in this case, we typically model this as a normal. That's the typical approach. So we say that the prior distribution is a normal with a mean and a certain variance. Okay. So that's the, and again, typically we remove everything which doesn't, we get rid of everything which does not depend on theta, and to compute the posterior, we just multiply the prior, or we say that this is proportional to the chunk of interest in the prior and the chunk of interest in the likelihood. We clip them together, and then we recognize again a normal. As I said, that would be what we would try to do. So multiply the likelihood times the prior, get rid of everything which do not depend on the parameters, and hopefully recognize a distribution. But this is unfortunately this is not frequently the case. But in this case we can do it, and again we get a normal posterior, which is convenient in this case. Okay. So and then the posterior summarizes all the information available, and we use it to solve the usual problems in statistics and in machine learning. Sometimes we just want to do a point. We just want to provide a posterior a point estimation, and we could use several versions. In this case, they concede because the posterior was normal. Okay, so in this case, we would use the posterior mean, right, which is here, and then we reflect something which is we mentioned the other day, which is that we get this point estimate is a mixture of the prior and the data. So here we have that we get the posterior mean as a weighted average of the prior mean and the maximum likelihood estimator, right? And we can observe in this example again something that we mentioned the other day, that as the sample size grows, these weights moves to 0, converges to 0, and this converges to 1. So this means that this estimation asymptotically it's close to the maximum likelihood estimation. And this is actually a pretty general result. It's a pretty general result. It doesn't happen always. It requires some conditions, structural conditions, but it happens in many interesting examples. So remember that in general we could summarize in a point estimate in other ways, like the posterior median, posterior mode, but in this case they are the same. Okay, in Bayesian inference, we could summarize the posterior with an interval, and we call it credible intervals or posterior probability intervals, right? And as we discussed, we could use symmetric intervals or high posterior density regions, but in this case, they concede, right? Hypothesis testing is quite different. So that would be the problem with which we started. So we were saying, is the average size of the capture pieces smaller than 5.5 or bigger? That would be the typical question. And in general, except in some specific cases, how we proceed is by computing the probabilities, the posterior probabilities of this hypothesis. Remember that there could be like 3 or more, right? And then one criteria would be to declare that evidence supports the in this case the null hypothesis if its probability is bigger than the alternative. So equivalently, if the probability of the null hypothesis is bigger than 1/2, we would be accepting the null hypothesis. And again, something that which is quite important to take into to consider is that the utilities or the losses do not need to be 0,1 or 1,0, and therefore this leads to more general approaches. We can generalize this, take into account costs, etc. and we can frame this everything within decision analytic frameworks that we shall revise. Yeah.
Before you change.
Yeah.
What was X there?
Sorry.
X. What was it?
X. Yeah. That these are the data. X1, X2, Xm. So I'm summarizing like somewhere. So all these guys, I'm summarizing it as a data.
Yeah, and is there a difference between underlined X and not underlined? Like in the first one.
Yeah.
X.
Okay. Yeah. I'm sloppy with my notation. Yeah. It's data. Given the data. Remember, just read this like data. Yeah. Okay. So let's say this was like the typical problems in typical statistical problems that are of interest to scientists in machine learning. The focus is more, as we have been discussing, is more on prediction or in forecasting, right? So in the same vein as we did the other day, the key for this is just the predictive distribution. So remember, we made this reasoning that we shall repeat a few times. So basically, we were saying that's the model for a new observation. So we were saying should we know the parameter that would reflect our prediction, so that and reflect our uncertainty about the prediction, right? But we don't know the parameter. We have uncertainty about the parameter, which is all the information or the uncertainty that we have is modeled through this distribution. So what we do is integrate out this uncertainty, right, in such a way. And this is what we call the predictive distribution. And this will be the thing that we shall use to make predictions. So I insist that rather than doing point predictions, what we are doing is providing a whole distribution to predict what is going on, what is going to happen in the future. And as with these examples that we've been using, in these simple models, we can actually compute this in the case of this normal and this normal. So we can see that, yeah. And sometimes we want to summarize. We want to summarize for the purpose of communication the predicted distribution. So we summarize it with the moments and so on, right? Okay, so basically that's the sort of introduction. Two problems that are pending is that we were assuming that the variance was known. So one question that we could formulate is what if the variance is unknown, right? So we were in these little examples that we mentioned, the variance was known, right? And another question is that we have just considered a univariate case. So the question would be what with the multivariate case. And basically, we'll see in a minute. Actually, we're going to see now a couple of things that will help us to solve it. So you can try to do them once we've seen, right? So basically, if the variance is unknown, this is another parameter, and we try to come out with a prior and integrate basically with the same model. And in the multivariate case, this is, I mean, the normal is basically the same object, and you require the same types of manipulations. Okay. So we move to the next one, to the next chunk. I don't know if there's any questions on the online, right?
No questions.
Okay, so the next part that we are gonna do briefly are introduction to simple regression models, and actually these are already models of interest in machine learning. So we are actually doing a brief discussion of linear regression from the Bayesian point of view. right? And a brief discussion of logistic regression in a very low dimension, right? So remember that we make that joke that basically in machine learning, quite frequently we were ending up doing, in practical terms, we were doing logistic regression. So we are in that domain already, and we shall do this. I mean, we shall provide a, let's say a quick and dirty approach to logistic regression when the dimension, the number of explanatory variables is low. Precisely to motivate the need to introduce other methods that will come later on. Okay, so associated with this, there's a lab, and you can practice all that we shall say. So there's an example on linear regression, Bayesian linear regression in ornithology. And there is an example of logistic regression in related with a bioassay. Okay, so that's the kind of problems. Again, we will go through the concepts. There's a numerical example in lab, right? But the example here would be something like this. That's a pertinent problem for us old people, right? So there's a study of kidney function, for example, as in the example, and we have here the age of the person, and here is a measure which is taught. It's just an index. There's a number of variables that represent or measure the function of the kidney. And there's a measure which summarizes the integrate. So something like the BMI that we discussed, which integrates weight and height, right? So what we have is that we can appreciate here. We want to decide whether we want to study whether kidney function declines with age, and also we would like to say something about the decline rate. And this is we do these kind of things because this is important to manage kidney transplants. So that's quite important for the right. Okay, so first recall the linear regression model and the maximum likelihood. So that's what I mean the traditional approach in classical statistics and in standard machine learning. So remember that we have, for the moment, one response, and we want to predict it based on several explanatory variables. So the model is that the response is explained by a linear combination of the variables, right? And the noise, well, there's a noise there that I should have put there, right? And now the parameters in this case are the weights, and we consider as well these variants. Okay. So we write the likelihood. So we multiply the densities, these normal densities. I mean, we would remove whatever is not dependent on betas or sigmas, right? So we would remove some stuff, right? We would log, etc., and then we would recover the classical maximum likelihood estimators for the weights and for the variance. Okay, that's we saw that already, but we're gonna use this. That's the classic. Now in Bayesian inference, we would start with the model as before, right? Same stuff, right? And then we would put a prior, right? We discuss several examples of this through the days, right? But here we are putting a standard non-informative prior. So again, we want to convey the idea, or we want to make the study more objective, let's say, or we want to convey that it's a sort of new phenomenon, and we have not that much information. So the prior that we put here is this one. You can see that we say that the prior that we put over the weights and this variance is proportional to this quantity. And again, this one is an improper prior. It doesn't integrate into one. You can see also that you could think of this prior as the prior of beta given the variance, which would be a 1 here. So you can imagine that there's a 1 times this one. So 1 is a flat prior over the betas, and this is the prior for the variance. And this makes that when we compute the posterior, we want to compute the posterior. So we want to compute the posterior of the betas and the variance given the data. It would have this decomposition, right? And in this case, you can performing the same type of calculation that we did before. We can recover that the weights given the variance and the data have a normal distribution, right? And the variance given the data has another distribution. The interesting thing is that the parameters of the posterior are actually the parameters of the maximum likelihood estimate. So we have here the same the weights, and this square parameter is computed as in the estimate of the variance. So of the maximum likelihood estimate of the variance. And the thing is, therefore, that with let's say standard software, you could get these numbers and go ahead. And this is illustrated in the lab. And one thing that we need to focus on is that we don't need this kind of, let's say, analytical results. I mean, we could use this to, I don't know, build a hypothesis test about the weights or about sigma, or we could provide confidence intervals. One thing that we will do is that we can actually convert inference into simulation, and basically the approaches that we would follow is we would need to compute these estimates, which are provided by the let's say standard software, and then what we do is just a mechanism to simulate. So we just need to simulate samples from the variance, which is from this distribution, and then so we simulate one sigma, right, or sigma squared, that's equivalent, and then given sigma square or sigma, then we draw from this normal, and then we repeat. And with these samples, we can just do all the kind of all kinds of inference and predictions and etc. that we manage. Yeah, this is just a reminder. This is a sort of a reminder of the computational trick to perform. Compute this for this stage. Computing this, sorry, especially this one, right? Well, this one and this one, sorry. This is the trick to compute it efficiently. Okay. Now in this domain, remember that we said that this type of hypothesis tests were not always very meaningful. in this case, this type of hypotheses are quite meaningful because you want to say whether there is actually an impact of the ith variable on the response variables, and you test it by you do it by testing whether this coefficient is 0, right? And the alternative would be that the hypothesis is different to 0, right? And you could actually do it analytically, taking into account these distributions. But I mean, to pave the way for how we are going to proceed with the more complex models, I just want to illustrate how do we perform this in a simulation based. So basically, we need to sample to get samples from beta, right? So because we're going to talk, but to get samples from beta, we need samples from sigma. So basically, what we do is, let's say we decide to use based on certain computations, we decide to use 1,000 samples. So we generate 1,000 samples from sigma square, and then we generate. I mean, we do a loop in which we generate a sigma, and then given sigma, we can generate a beta using these distributions, right? And then what we do is for the beta that we are interested in, we sort that vector, and we could use an interval which is, I mean, out of this 1,000, we remove the let's say, for example, the first 50 and the last 15, right? Okay, and then we would just need to check whether there's the 0, the sort of value of interest, is in that interval. If it's in that interval, we would say that the evidence supports this hypothesis, and if not, it supports the alternative hypothesis. That's by the way, that's we are getting rid of 100 out of 1,000, so that would be an approximation of an interval of probability 0.9 for the parameter. Yeah, and again, forecasts. That's the interest in machine learning. So we want to, I mean, given new data, we want to make a forecast. What is the observer? So given that we have observed this, so given new data, what would be our forecasts? The forecast has this aspect, and it's the same type of trick. So given that we knew the parameters, that would be the predictive distribution, right? But we don't know these parameters, and therefore we use this. I mean, we need to take into account the uncertainty that we have about the parameters, right? Which is summarized with this posterior distribution. We integrate out that uncertainty, right? And that would be the predictive distribution, right? And you can actually do it analytically with this. We are still in the analytic world, right? You can compute that these distributions have in one case, given sigma, it would be a normal. If you get rid of sigma, it would be a T distribution. But the sort of type of thinking that we want to push, and because that's the world that we'll need to follow in more complex problems, is by simulation. Is performed this by simulation. So basically, in this case, we would need to, I mean, to simulate from the predictive distribution. We would just need to simulate the betas and sigmas, right, from this distribution, which is that's easy. It was before, right? And then given beta and sigma, we just need to generate an observation from this distribution, which is a normal, right? So given beta and sigma, this is a normal. So and that's very easy. And if we need samples, we just need to put it in a loop, and that's super easy. make then all types of predictive inference. Final comments. So in the intro ML, we talk a little bit on model checking, all the kinds of I think it was like something like 6 or 7 ways that a linear model or regression model could go wrong. So the same kind of things. But the good thing of this is that we can actually use simulation and compute the predictive distribution of all data summaries. So remember that we were using various types of data summaries. In this case, we can be much more informative. So that's quite good. And there's one example in the lab. Okay. So pending issues that we'll return to them is that the first one is, well, the second one, sorry, is nonlinear regression. This has been and this includes neural networks. So we'll have to come back a little bit later on this. The sort of change will be basically that we won't no longer be able to do these analytic computations. So we'll need simulation mechanisms or some other types of approximations. And the other thing is we didn't mention about hierarchical models, which will be quite important, which are quite important in various domains. But we'll return to this. Okay. Right. So the next one is, and this will sort of make it will be like an example in which we reach the limits with analytic computations, and we need to go to simulation almost necessarily, is with logistic regression, right? So that's the kind of example that we do. It's fully done in the lab, but it's the type of example would be, I mean, we are trying let's say a new cancer drug, right? And of course, before human testing, there's typically animal studies to find out what are the safe doses, right? And we undertake what are called bioassays, right? Experiments. And for example, assume that we study 10 groups of 11 groups with 10 mice with an increasing dose, and we observe the proportion of death. So we suppose that there's 11 doses, 11 increasingly higher level of doses, so from 1 to 11, and then what we observe is the probability or the proportion of mice who die. So at dose 1, no one dies. At dose 3, no one dies. But then I don't know. At dose 11, all of them die, right? So you can see this, and we can imagine this logistic curve, and we want to come out with the parameters of this curve for example, find out what is called the LD50. LD50 means the dose at which 50% of the mice die. So this is quite important in this kind of studies. Okay, this is done fully in the lab. We just explain the concepts and methods.
So sorry, what was the meaning of those dots?
Sorry,
the dots. What do they mean?
This one.
Yeah.
Yeah. So for example, here
that's group 7, right?
Yeah, at dose 4, right? So this is a very small dose, a very large dose of the drug. So at level 4, about 20, well, a little bit more, 30% of the mice died, right? So this is a very non-toxic dose. here this is super toxic, right?
Doesn't look very logistic though. It looks like it goes down.
This one.
Oh, that does.
No, that's what we see. Yeah. So I mean, with the eye, that's what we with this data. Of course, it's not perfect. I mean, it's an experiment, right? Sometimes it's right, but what we see with the naked eye or with a bit of imagination, we see that's the logistic, and that's what we try to fit, right? So just that's the MLE. Just to remember that we did this in the other sessions. So, but just to remember, in case somebody didn't come. So basically, these are the explanatory variables. In our case, would be the dose. This is the number of trials, number of mice that were treated, and this would be the number of successes. In this case, is the number of mice dying, right? And we do this at k levels of this one, right? So the model is given the parameters. The parameters are alpha and beta, right? It will be alpha and beta. Well, sorry, given the proportion. So this is a binomial experiment, right? And what we formulate is that the parameter, the success rate or the proportion is related with the explanatory variables in such a way. So we have this logit of the parameter is related with this linear function, right? And the logit is the logit is the log of theta. I mean of the odds, right? Yeah, of the odds. And the inverse is called like this. So the parameter is expressed in terms of the logit of the explanatory variables like this. This is just the likelihood. So it's in the k experiments, the product of the probability. So it's this is a binomial. So this is the probability, the number of successes, 1 minus the probability, the number of failures. And as usual, we log this, and then we try to maximize, and we get the corresponding alpha and beta. That would be the maximum likelihood. And of course, just to do this, we would need typically an optimization routine to get it. That's not true. Now, in case of if we perform a Bayesian inference, we just put express the sort of scheme, the general scheme. So we would have the likelihood as before, and then we would, given a generic prior, we would have a generic posterior, right? And the expression would be the posterior, the distribution of these parameters given the data, right? And we would be the prior times the likelihood, right? And the thing is that now this is there's, I mean, no way to compute the posterior analytically, right? But we can just for this. So let's say that we have reached our limits, right? But we can have a quick and dirty approach, which is described here, but it's better to explain with the example, with the numbers. This is in the lab, right? In the lab, right? But basically, what we do is somehow we try to find out where is the posterior concentrated, right? Here we are displaying the posterior in terms of alpha and beta, right? So we can find out where is the, I mean, around it's sitting close to the MLE, etc., some kind of grid. So what we do is then we can make a grid, right? Like this, and pick one point one representative point of the Greek of the grid, right? Of each little square, right? Of each pixel, if you want. And then what we can do is so we have got the region, we got the grid. What we can do is evaluate the posterior at each of these points, right? And then approximate the density at each of these. I mean, we give the same density at each of these, at each of the points of this square. So we evaluate here, and then we give them the same density here, right? So we have at each of these at each of these squares we have a density, right? We can normalize, and then we can generate points from this distribution, which will be reflected here. There will be repetitions, and therefore what we can do is jitter this sample, and that would be this would give us a sample from the posterior. So this is a very difficult. This is a complicated object to handle, but in this way. Get a region, choose a grid over the region, evaluate the density over each point in the grid, and then get a sample. We can handle. So this would be a sample from the posterior, right? But this is, I said, I mean, this is quick, but this is dirty because it works only on very low dimensions. In this one, we had just one explanatory variable and two parameters. If we go to 2, 3, 100, it wouldn't be very efficient. Okay. And as an example, remember that we were saying we wanted to find out the LD50 doses, right? So we can use this sample. So these were samples from alpha and beta. We can use these samples to find or estimate the LD50, right? So in this case, we make some computations to find out that the LD50 dose has this expression. So all that we need to do is compute the posterior or let's call it it will be the predictive expectation given the data, right? So since this is this is the LD50, has this expression. The only thing that we need to do is get a sample from alphas and betas, and then make this approximation of the mean, right? So we get we get a sample from this distribution, and then we use this mean. So we could use this sample to find out the doses, and this is done in the lab. If somebody wants to practice or learn a little bit about it. Some pending issues that are left, because I mean we need stronger tools. That's the idea. Is that what we just did with one explanatory variable, logistic multiple regression. We'll be able to do it a bit later. As I said, the quick and dirty approach would explode in hierarchical models. Again, we could have various experiments that can be related somehow in a hierarchical manner. And other GLMs, for example, we described logistic. We could do probit or other. So logistic is of more interest to biosciences. Probit are of more interest to economists, etc. And we'll see tools to be seen. Okay, that's it for today. Any questions or comments? So I think I'm hungry.